Okay, thank you. Let me share my screen. So by the time, can anyone like would like to brief on what we have been discussing? Anyone would like to dis describe a bit on what we have been discussing? So we have been discussing in the last week about sedimentation process, right? So what is sedimentation and what are the considerations we have made so far? Anyone? So sedimentation is a process where we allow so here we allow the settling.
Sedimentation is the process of settling the solid materials at the bottom of our settling tank.
Yeah, correct.
It is otherwise called as a sedimentation basin. Sedimentation
Of the
basin
clarifier.
clarifier or the settling tank. Mostly the solid particles are settled because of their gravitational force, because most often they are using that gravitational force. There are the various types of sedimentations are the discrete particle settling, flocculation settling, hindered settling, and then the compressed particle settling. So for this
Yes.
discrete particle settling means the particles are settled as individual particles. For flocculation settling means you have to add the flocculating agent, so it can be settled in the form of the bulk materials.
Yes, very right. So
Hin-
yes, carry on. You were saying something. Okay, so what she has meant. Sorry, you are not audible. Yeah, so what she has mentioned is very correct, and we have seen types of sedimentation basins as well, horizontal or vertical upflow clarifier, right? So yeah, what we had assumed is in any sedimentation tank, we allow uh, sufficient time for all the particles to settle well. Also, there is like each of the particle gets equal time inside the basin, and they get the equal opportunity for settle, and velocities at all time point or at any point in the basin is also same. And inside a basin at every point, um, there is equal driving force for settling, and there is no turbulence or no channel, not channeling, but yeah, so all sorts of ideality we had seen, but in real practice or in real scenario, uh, ideal word or ideal thing does not exist. So there could be some non-idealities in any uh, industrial process. So similarly, in sedimentation basin also, there could be some non-ideality existing. So what could be the non-ideal behavior that you can observe um, in any basin? So one is, in any sedimentation tank we usually provide gentle mixing, right? So that it not it will have mixing also, so that the concentration is uniform, but it also gets time and enough, like the force or the energy provided by the turbulent or the mixing is not enough to like it will not hinder the settling, right? So in that case, uh, we have we design any sedimentation tank for a particular amount of or for limited Reynolds number. Now, can you tell me what is Reynolds number, and what does it tell about?
Reynolds number is defined as ratio between inertia force and viscous force.
Yeah, and how is it related to flow patterns, or in our case flow behavior? Yeah, so these discussions will help you revise whatever you have learned, and it will give you some better insights. So you can always participate. Yes.
If the Reynolds number has a particular value, for example, if it is less than 1000 or greater than 1000, we can identify which sedimentation it is a settling.
Your voice is breaking, but you were in the correct direction. So, yeah, so there was some network issue from my side. But sedimentation, yeah, yeah, you are correct. Reynolds number is nothing but it gives us the idea of flow behavior. If we talk about the value of Reynolds number, then Reynolds number
Less than 1000 means turbulent settling.
1000 is laminar flow. So there are different things. Rho Vd by mu is the formula for Reynolds number, right? So here we consider how, uh, you know, this means that more the velocity, faster will be the flow, right? Now, let's say if we have two liquids, one is water, another is oil, right? So here water has low viscosity Oil has high viscosity. So viscosity is nothing but, it is sort of resistance to flow, right? So that is why for any flow, uh, like resistance to flow, if it will be more, uh, Reynolds number will be more because it will resist the flow, right? So here, if the fluid has high viscosity, it will have lower tendency to flow. So there are three regimes for Reynolds number. So in practical life also, if you will observe, water will easily flow as compared to oil, right? So Reynolds number, there is one, laminar, transition, and last is turbulent. So there are three different regimes where you see laminar means, you would be knowing that there are, for any fluid there are these, layers in which fluid is, uh, assumed to flow. Like let's say, this is the surface, solid surface. So now the adjacent most layer, it will, let's say, have this, uh, profile of flow. So all the subsequent, uh, layers will flow in a similar manner, right? And there is no change in the flow lines or flow pattern in, like, in the entire cross section, right? But however, if you, look into turbulent flow, then water current can be any, like it will have a lot of mixing because of random and, fast movement of, water molecules, right? So this is the fastest motion, and this is the, like, uh, very less flow velocity, right? So you have, the flow lines of water, each layer flows, uh, in similar way and it stays there, right? So if there is turbulence, uh, it can have, you know like, whenever we design a sedimentation basin, it is usually designed for laminar flow region because we want gentle mixing, right? So if there are zones where, you will be providing here an impeller or any sort of thing for gentle mixing, right? But this impeller will have some active area where there will be higher mixing and there could be some higher turbulence, while there will be regions, for example here it is turbulent, and there will be regions where it will be laminar, or you can have, you can say there is a dead zone where you have very minimal mixing. So such sort of non-uniform mixing can also happen, and some, zone where there is turbulence and some zone where there is laminar flow. So it is, very difficult to maintain the flow, and hence non-ideal behavior comes into picture. So whatever efficiency you have designed, like the basin is designed for, you will not be able to get the similar, efficiency practically, right? So that is there. Next is energy dissipation. So in any sedimentation basin, you have, a lot of energy dissipated, at various points. So can you tell me what does this mean?
Density variation.
No, right now I'm talking about this, uh, energy dissipation. Sorry, I got exited from the meeting. Let me share my screen. Yeah, so why is there energy dissipation? So for any, like, there will be millions of liters of water treated in any industrial plant, right? Uh, so to we require a lot of energy by using pumps. Like, it these are nothing but very heavy pumps which allow flow for millions of liters per day, right? So these heavy pumps, they supply energy to water, and that water uh, will be pumped, like, right? So for passing from one point to another, or for taking one uh, height to another height, you are providing energy in any form. For example, kinetic energy for flow, and potential energy to take it to another height, right? So you provide energy by using pumps. Now whatever the energy you have provided, it's very high, because uh, for the flow inside any pipe, you do not want settling in the pipe itself, right? So what you do, you provide very high turbulence so that they are highly mixed inside the pipe. So let's say this is the pipe for inlet. So inside the pipe, they are so much in turbulence, so that they do not mix, or sorry, they do not settle, and they are completely mixed. And when they if at such a high velocity they enter into a sedimentation tank, they will not settle, right? So what we do, we provide some baffles so that its high velocity inside the pipe is restricted, and it is reduced to a certain level, so that it falls under the settling zone, and it falls under the laminar uh, regime, right? So its velocity is reduced, and during that time, uh, when the water is, like, the flow is obstructed, a lot of energy is dissipated, right? And again it is required, so by providing baffles, you are restricting the flow of solids as well. That will again enhance the sedimentation. So you can say a lot of energy which was supplied to the flow, it has dissipated and it has wasted. Next is density current. So yeah, anyone would like to tell what it is?
It occurs due to the difference in the density. Due to the difference in density, short circuiting occurs if
Yeah.
the tank is not uniform.
Yeah, so you can say the tank is not uniform, and there will be concentration gradients, there will be non-uniform concentration, also the changes in temperature, right? So as you mentioned, density is different. Now what could be the reason for difference in density? One major reason is temperature, right? For example, surface which is exposed to the atmosphere might have some different temperature, and surface, for example, if there is an impeller which is rotating, so it can dissipate some amount of heat, right? So let's say that much heat causes uh, some local heating of water, so that is nothing but temperature gradient uh, in the tank. Now another could be, if you are operating sedimentation basin during, let's say, in winter season or in summer season, there could be minor variation, or few degrees of 1 or 2 degrees of variation in the temperature, that might change the local density, or slight changes in density, and again it can affect the settling. And last is wind effects. So as we know that wind, like since the sedimentation basin is open to the atmosphere, so wind can also affect the movement or the motion of uh, uh, fluid in the basin, and it can also cause scouring, right? So which is resuspension of the settled uh, particles. So these type of non-idealities are very common, and you should like take into account all these while you are designing or while you are finalizing the dimensions of any basin, right? So yeah, next is design of any basin was discussed, where like there are thumb rules which you need to follow at all points while you are designing. So for designing any instrument or any tank or reactor for any industry, there are a lot of thumb rules that are followed every time, right? So these thumb rules will provide you the basic guidelines, but obviously these thumb rules are also based on some ideal behavior of that reactor, of that basin, of that tank, right? But in real scenario, that is not possible. So again, the next thumb rules which will be provided will be for the considerations of the non-idealities, right? So for example, if we are designing a basin, right, so an important parameter right, uh, could be the inlet flow velocity, such that it will fall in a particular laminar regime, and it follows a particular Reynolds number, right? So for that, there will be a range of velocity or inlet velocity that you will be following. So that guideline will be provided, like what should be the range of inlet velocity is provided, so that you will have minimal non-ideal nature, right? Next, an important parameter will be, let's say, the depth of the tank and the dimensions, right? So for any basin, you will have particular, let's say, you based on theoretical calculation, you are calculating some depth. Now obviously your tank will not like in practical scenario, it will not um, uh, work up to the mark, which, like, it will not give you efficiency what you are getting theoretically. So zero point 0.6 meter, which is a thumb rule as mentioned in the lectures also, so that much amount of um, buffer, or that much amount of extra depth you always need to add to encounter all sorts of uh, non-ideal behavior, or any shock in the let's say flow, you are having sudden shock in your uh, wastewater also that is coming, right? So you can have more flow rate to handle, or you can have more concentration of suspended particles to handle. So also all sorts of uh, sudden shock or non-idealities that will take into account. So similar thumb rules you will be required to go through, and the major thumb rules I have already mentioned right now. Yeah. So next question, next is numerical, which is based on this uh, design of a basin, right? So basically you are calculating the dimensions of a basin, and you are checking at all points, you will be checking what, like whether uh, the assumptions that are made are fulfilled or not. So uh, yeah, so till this point, is it clear?
Yes, ma'am.
So let's quickly talk about how do we proceed in any numerical, or how do we calculate the dimensions and make all the checks at every point. Yeah. So first question is, like, the numerical is, just a minute. Yeah, so design the settling tank for a town which have CTP with the design overflow rate of 16 meter cube per day per meter square, and the maximum day design flow is 21,600 meter cube per day. Assume the water temperature of 15 degrees Celsius and the column depth of overflow rate is 2 meters. At 15 degrees Celsius, the viscosity is given by this. So you need to give the dimensions of the tank, right? So first is, what is overflow rate? Now if you look into the unit, it says it is the outlet flow obtained, right? Overflow rate is nothing but whatever the amount of outlet flow you are getting from a basin. Now it has unit of meter cube per day per meter square, which means flow rate per unit area. And it is said that maximum capacity or the flow design capacity is nothing but 21,600 meter cube per day. So if you will divide this flow rate by this value, okay, so flow rate per unit area you have. So if you divide these quantities, what you will have at the end is the surface area of the tank, right? Now again, there is a thumb rule that you will not have only one sedimentation tank, but you will have at least two tanks. And here, if in exam also you are asked, minimum two tank you can take. And next is, if anything is not mentioned in the question, you can take any number as your assumption, and that you can mention as the assumption made for this particular numerical. So yeah, for this question, let's take 6 tanks as a trial, right? And this process is also again iterative depending on the length required, right? So there are thumb rules for length to width ratio, there are thumb rules for velocity to be maintained. So if for any assumption of your number of tank, all these values are under the permissible limit, then you can proceed with the particular design that you have made, particular assumptions that you have made, right? So let's start with six tanks. Okay, so this is the total area which is required for this much capacity. So if you have 6 tanks, then the area needs to be uh, divided, right? So 1350 divided by 6 tanks, right? So per tank you will be required 225 meter square per tank, right? So now let's calculate the dimensions in terms of width and length. Now you need to assume one of the parameter, right? For example, maximum width you can have is 6 meter, right? So we are assuming here 4 meters for safer side per tank, right? So the length per tank will be uh, length will be area per width, that you will get length, right? And length to width ratio you are getting is 14.1 is to 1. Now there is a thumb rule that length to width ratio should be greater than 1, and since here you are getting 14.1, it is acceptable range. Now the depth of the tank you are given as 2 meters, but you need to have 0.6 meters of margin, and additional 1 meter is also required, so total of 3.6 meter depth you are getting. And the length to depth ratio, again, you are if you are calculating, it should be acceptable. Now to calculate again the flow regime, you need the velocity, right, value. So flow rate per unit area you will be calculating, and so area is nothing but velocity is horizontal, right? So this is the direction of v, and for that you will need cross section area. So cross section area nothing but, let's say this is the tank and this is the flow, right? So this is the cross section area. So this is nothing but depth, right? And this is nothing but width, right? So depth into width will give you the cross section area, and for all the tanks, 6 tanks, so this is the velocity. At every point you need to have a check whether it falls in the acceptable regime, right? And now check for Reynolds number and the Froude number, so that uh, you can see whether your assumptions made are correct, and if these all assumptions are correct, then the given dimensions are acceptable, right? And the given design is acceptable and you can use that design. Is it clear so far? Yes, is it clear? Anyone?
Yes, ma'am.
Okay, let's proceed. Then you have so this was conventional sedimentation basin. Then you have high rate settlers, right, where you are allowing the settlers to have higher surface area, and the higher the surface area, higher will be the settling efficiency. So in any case, you will be able to, like within the same area, uh, or you can say with smaller area, you will have better efficiency, right? So what you are doing, you are having uh, parallel plates or parallel tubes which are inclined, so that particles they slide down, or in case you are having two horizontal plates, so the particles will have smaller distance to travel for settling, and hence you can say the settling will be faster and more efficient. So this is nothing but high rate settlers. Yeah, so moving forward, this was about the sedimentation. Let's talk about filtration now. So filtration is nothing but channa, right? What you say in Hindi is channa. If you have solid particles, let's say in tea, so you want to separate tea from the liquid, you will use a strainer and you will pour the tea so that over the strain the tea particles will be uh, separated. Another thing you can have is like there could be multiple mechanisms for filtration. This was one such example where you can say filtration is taking place. So it is nothing but a mechanical or physical process where you are removing suspended or colloidal particles. So this filtration is using a medium which will obstruct the path of suspended or colloidal particles, and it will cause the separation. So for that you can have first is fixed bed or a bed of granules, porous granules. Let's say this is the granules bed. So there, and if you zoom in, this will have a sort of void spaces across which water will flow, right? Let's say now you have uh, suspended particles of this sizes. So this type of particles, they will not be able to pass through the granules here, and that is how they will get separated in the interstices between the granules, right? Yeah, so there could be number of designs for filtration. There could be mechanical straining. There could be rapid, slow and rapid. Yeah, it's here. Sand sand filters. There could be filter media where absorption takes place. There could be membrane filtration, right? So if you talk about a basic filtration unit, then let's say so let's say you can have fabric filters or plate and frame filters or sand filters. There will be a deposition. For example, this is a plate and frame filter where you are using fabric as the filter media, and let's say you will have pores across the fabric which will allow only water to pass through, but the solids will deposit on the surface of fabric, right? So this is the most basic example of filtration. Now when solid is depositing on the surface of this fabric, what happens is as the time passes, more and more solids will settle. Now this layer of solids which are depositing on the surface of the filter is nothing but known as cake layer, right? So this is known as cake layer, and this cake layer obstructs uh, yeah, so more the thickness of this layer, more will be the resistance to flow, right? So for example, you are this cake, it will water will have to pass through more and more thickness of this cake layer as the time proceeds. So there could be two sorry, this would be pressure here. So there could be two principles. Another is if you want constant amount of volume to be treated or constant amount of clear water to be obtained, more and since the cake layer is thickness is increasing with time, so if you want constant volume of treated water, you need to supply more energy with time so that you will have same flow, because otherwise this will create pressure drop and the flow will be resisted and you will have lesser amount of volume passing per unit time, right? So flow rate will reduce. So more energy with time needs to be provided to maintain the flow rate, right? And the efficiency. Contrary, if you have a constant pressure, which means you have constant energy supply, then you will have a reduced volume obtained at the end, right? So these are two principles which uh, operate. Then again, there could be number of factors that affect the filtration, as we mentioned that one is resistance by the filter media. So more the resistance, more will be the efficiency, but lesser will be the flow, right? So it's all contradictory. Like yeah, another is cake compressibility. So if you are able to compress the cake in smaller thickness, more amount of solid will be deposited, and if it is more compactly packed cake layer, then it will provide more resistance, right? So you need to provide more amount of energy by pumping for water to pass. Another is the amount of pressure that you apply on and the cake thickness, also the temperature, the particle size, concentration, these all affect the efficiency of the or the process, right? Now next is for any filtration process, let's say if you are using any bed porous granule bed, sorry. So here you can have some random shape of particles or granules that you have used as porous media. So in that case, the calculation might be difficult and the surface area changes, right? So what we do, uh, for shapes, for particles or granules having different shape, they behave differently in terms of pressure drop, in terms of flow patterns, right, across a filter media when they are packed. So to get the idea how will be the flow pattern as compared to, the most ideal one is spherical, right? So these are complete spheres, but ideally what we have is some random shape, right? So we can have any sort of shape. So to encounter the shape effect, there is one terminology which is known as sphericity. And sphericity is nothing but uh, you are considering that granule, the considering the area of granule which is occupied for the same volume of that same volume occupied by sphere, right? And when you take the ratio, it will be sphericity value. And this sphericity value will help you in calculation of for any uh, uh, not only filtration, but any process where fixed bed uh, reactors or fixed bed columns are used, then pressure drop is an important factor which needs to be incorporated, right? So you cannot allow for a pressure drop above a certain limit, otherwise the flow will be restricted. So this sphericity again will help in calculating the pressure drop as well as the velocity across the bed. So there are a number of terminologies which you can look into the class, where the formulas are important for numerical and velocity of fluid across the bed, and on what factors do they affect. It's the hydraulic radius, and also the this is nothing but there are various equations and they are named based on the scientists who have discovered. So this is nothing but velocity of fluid across the bed. Then if you talk about Poisson-Kármán equation, it will help you get the knowledge of hydrodynamics across the bed, and it will give you the pressure drop value per unit length, which is dependent on uh, the porosity or the void space, the diameter of particles, uh, the sphericity, right? Then the velocity or the mass flow rate, etc. Right? So all these factors, they affect the density. Now, what will you do if you don't have uh, spherical particles? How will you calculate the diameter? Can you tell me?
Pi by 4 d square is equal.
Sorry. If you don't have spherical particles, what diameter value you will be taking? Do you have any idea? Like in case of sphere diameter, it is very simple to calculate, to measure, right? You would have learned in your 11th 12th also 1 year caliper. You can easily measure the diameter of any particle, even if it is in size or millimeter size range. So but if you have non-spherical particles or randomly shaped particles, how will you uh, do? Yeah, so that is where sorry, that is where sphericity comes into picture, right? So it gives you the idea of how much closer the granule is closer to sphere, right? And let's say its value is zero point 0.6. So it's for let me just tell you. So for sphere, phi value will be equal to 1. So more the lesser the phi value, lesser is the uh, spherical nature, right? So to calculate the dp value, you take, for example, you calculate the volume of uh, the granules. You get the volume data of the granules. Then for that particular volume, uh, you choose it as pi by 4, uh, sorry, 4 third pi r cube, right? So 4 third pi r cube. So this will be the equivalent volume of sphere if they are present. So now calculate the dp and correspondingly calculate the phi also. So that dp that you are getting, that you can use here in the formula. So you are calculating dp as if the particles are nothing but sphere, but to incorporate that they are not sphere, you are using this value, sphericity value. I hope it's clear. Next is depth filtration, uh, which is nothing but performed by passing the liquid through the filter bed, right? And As I mentioned that the performance of any filter is determined by the amount of particles removed and also the head loss or the pressure drop across the bed. And how do you calculate the pressure drop across the bed? You have Cosny-Kármán equation which helps you calculate the pressure drop across the bed. Uh, yeah, so this is the and there could be number of flow patterns across the bed, which is conventional downflow. Then you have deep bed downflow where you are providing more depth so that you have better settling or better or you have more depth of the bed, which means more separation, right? Then you have deep bed upflow continuous backwash filters. So what does this mean? Usually if you say to save energy, downflow filters um, are used, but downflow filters means there could be some random motion of fluid across the granules. And do you know what could be the flow pattern? So if you zoom into any porous granular bed, then the granules will be randomly arranged, right? And the void spaces between two granules will be always different, right? So it can have, let's say, this is one granule, this is another granule, this is third granule. So let's say this two granules has different space as compared to this two and as compared to this two also. So where will the fluid flow? So the fluid has tendency to flow um, through that area where it has least resistance, and where it will have least less resistance, where it will have more space to flow, right? So it will flow like this and this. It cannot flow like this and this because it has higher resistance. So this is the tendency if sorry, the water is allowed to flow under gravity. But in case of and this phenomenon is nothing but known as channeling, right? So the flow is very random and it flows across that path where it has least resistance. To minimize the channeling, we have usually upflow behavior, where in upflow manner the water needs to be pumped because water in the anti-gravity uh, it does not flow, right? So you will pump it and it will have lesser channeling. So that is deep bed upflow mode. And next is you can have pulsation effect so that more settling uh, is obtained, and pulsation can be obtained by allowing air to pass, right? So this was about depth filtration, and next is you have membrane filtration. So what is membrane filtration? Membrane filtration is nothing but you provide a permeable membrane. uh, do you know how a permeable membrane looks like and what are the applications of a membrane?
Semi-permeable membrane are used in osmosis process. In our house, we are using the reverse osmosis process that it also contains one membrane.
Yeah, you are correct. Very correct. So, if you look through your naked eye, it's not it. You can visualize it as a piece of cloth, or you can visualize it as a piece of paper. It will look similar to that, right? But if you visualize under a microscope, it has small pores, right? And if you see those pores, So that pores will not allow, depending on the size, it will not allow the particles which are, or anything which is bigger than uh, the pore size. So let me show you how it looks like. So SCM images will give you the surface, you know, image, right? So you will be able to visualize the surface. So these are nothing but the pores, right? So this is the structure of a membrane when you look under a microscope, and you will be able to visualize. And the dimensions of these pores depend, and you know, so this much is, let's say, 0.1 mm. Yeah, so this is a microfiltration membrane, and there are, depending on the pore size, you can say uh, the membrane can filter different things. So let's see that. So let's say first is microfiltration, and microfiltration means the membrane will have pore size of microns, which is ranges from 10 micron to 0.1 micron, and anything which is greater than 0.1 to 10 micron, they will get separated. For example, suspended particles you can separate, right? So here is the list again of what you can separate. You can separate emulsion, you can separate bacteria, right? So through this membrane you can separate that. Then is, if you want to further separate anything which is smaller than that, so you will be using ultrafiltration membrane, where this is the particles pore size range, and anything which is greater than this can be separated by the ultrafiltration membrane. And then we keep on decreasing the uh, pore size, and you can have smaller and smaller particles. Now again, if you further go smaller, then you will be able to separate the ions as well, right? Not just the suspended particles, you will be able to separate divalent ions, you will be able to separate monovalent ions, protein, which are actually molecular scale, right? So they are not visible by your naked eye, but they are at molecular scale of few uh, nanometer size range. So those also can be separated, and this is nothing but reducing size range. uh, so if you depending on the size range of pores, if you classify membrane, first is microfiltration, next comes ultrafiltration, then comes nanofiltration, and then comes reverse osmosis, which you mentioned uh, are used in our household, right? And it can remove all sorts of monovalent ions, even monovalent ions, divalent ions, all sorts of impurities it can remove, right? So that is why it is used in our house. But again, there was a controversy that if reverse osmosis is removing monovalent and divalent ions, even which are nutrient also to our body, um, such water is not healthy for us to drink. So again, nowadays household filters, they are, after the RO unit, they are putting one unit which adds the nutrients again back to the water for us to have healthy water to drink, and to provide us nutrients for our body, right? uh, but yeah, so as the pore size reduces, so this way pore size reduces, and since pore size reduces, you need to apply more energy for water to pass through, right? Because since you are not allowing the particles or even ions to pass through, you are again resisting water also to pass through, right? Because the pore size is so small. So which means that moving down, you are you need to apply more energy by means of pressure, right? So you need to apply more pressure as you go on increasing the or sorry, as you go on decreasing the pore size. So this is what it is mentioned. And yeah, so if is that clear to you all? Okay, if so, let's move to the assignment. First question is, a non-uniform horizontal velocity in the settling zone in is an assumption in discretely settling particles. Yeah, what should be the answer to this question? Okay, so here it's a false statement, right? So for discretely settling particles, we assume that it's uniform velocity for all the particles, right? So the statement here made is false, which states that it's non-uniform velocity. Next is, what is the x in the figure for settling zone? So this is nothing but a sludge blanket, and from the options, sludge zone is the correct answer, right? Next question. Stop me wherever you have doubt and just let me know if you are with me. Um, yeah, Lamella settlers are also known as dash. Lamella is another terminology which is used for plate settlers, right? So correct answer is plate settler. Next question is, if the cake is rigid and incompressible, the compressibility factor S is dash. So as the name suggests, compressibility factor is nothing but uh, more you are able to compress, more will be its value, right? So for rigid and incompressible fluid, its value should be 0. Next question is, if the cake is composed of incredibly soft and easily deformable particles, then the compressibility factor of cake S is equals to dash. So here you are saying that the cake is so compressible, you can easily compress it, right? So which means that its compressibility factor should be 1. Next question is, as the thickness of cake increases with time, the rate of filtration dash. So as the thickness of cake increases, more resistance it provides and it reduces the flow rate, right? So the rate of filtration reduces with time because there is a lot of pressure drop observed. Next question. The ratio of surface area of equivalent volume of sphere to the actual or true surface of the grain is known as dash. So this is nothing but sphericity, which means that how close your uh, granule or your grain is, how close to sphere. Next is, membrane filtration can be broadly defined as a separation process that uses a dash membrane to divide the feed stream into two portions, permeate and retain it. So the correct answer is semi-permeable membrane, right? Are you following me? Uh, Sorry, I logged out somehow. No, the class is not over. I somehow got disconnected. I didn't know. Can you tell me at what question? Like I have been discussing assignment. So at which question like could you hear last? Yeah. So I was discussing the assignment. Can you tell me the question number where I got disconnected? Yes, anyone? Please let me know.
We talk about the filtration, ma'am, micro filtration, the nano
Okay, so
filtration
that was
process.
over, right? The
Yes,
filtration
ma'am.
using membrane. Okay, so I will again discuss the assignment from the beginning. Like these are nothing but short questions only.
Okay.
Okay, thank you. Yeah, so the first question is a non-uniform horizontal velocity is the set in the settling zone is an assumption in discretely settling particles. So is it correct or false? Yeah, the answer to this question is false because discrete particles have uniform velocity in the settling zone, right? And they settle at a constant uniform terminal settling velocity. So the answer is false. Next is what is x in the figure for settling zone? Yeah, so this is sludge blanket, which is nothing but sludge zone, right? Am I audible? Next question. Lamella settlers are also known as dash, which are nothing but plate settlers, right? So that is nothing but another name of this. Next is if the cake is rigid and incompressible, the compressibility factor of cake S is equals to dash. Now compressibility factor, as the name suggests, it will be more if the cake is compressible, and if it will be less if the cake is not compressible. So more the compressibility, more will be the value, right? And here the it is mentioned that the key term is it's rigid and incompressible, which means its value should be 0. Next question is if the cake is like it's the opposite. If the cake is composed of incredibly soft and easily deformable particles, then the compressibility factor will be dash. So it should be equals to 1, right? Next question. As the thickness of cake increases with time, the rate of filtration dash. So this we have discussed during the class that as the cake thickness increases, water needs to travel more distance, which is the more thickness of cake, and since it are solid particles it resists more, right? So more the thickness, more will be the resistance, and the amount of water filtered will be less, and hence the rate of filtration decreases. Next question, the ratio of surface area of equivalent volume sphere sphere to the actual or true surface of the grain is dash. So that is nothing but uh, like this is the definition of sphericity. Next question is membrane filtration can be broadly defined as the process that uses dash membrane to divide the feed stream into two portions, uh, permeate and retentate. Answer is yeah, answer is semi permeable membrane, right? Next is,
Screen, ma'am.
sorry?
I'm unable to see the screen.
Oh,
Question I'm
sorry.
not unable to view.
Sorry. Should I repeat the questions then? So sorry. Uh, yeah, so were you able to follow if my screen was not visible? Like, since when was it not visible? Or should I repeat? There are only two questions now. Actually, the questions are simple. Uh,
Fourth onwards, ma'am.
sorry.
From fourth question onwards.
Yeah, so this is the fifth question. If the cake is soft and deformable, what should be the compressibility factors? Oh, answer is 1, right?
One.
Yeah. Next is, as the cake thickness increases, the rate of filtration should uh, reduce, right? Because it provides more resistance to flow. Next question is, the ratio of surface area of equivalent volume of sphere to the actual or true surface of grain is nothing but sphericity, right? Membrane filtration can be broadly defined as a separation process that uses dash membrane to divide feed stream. So it's a semi-permeable membrane. And what does this mean? It selectively permeates some portion of the mixture, and it selectively rejects some portion, right? So depending on what you want to separate, you choose a membrane, because there are a number of types of membrane with varying pore size range, and also they have different materials, and depending on the material, some material, for example, they are suitable for larger temperature application, and some are not, right? So depending on the application also, you choose the membrane. Next is a mechanical or physical process of separating suspended and colloidal particles from fluid by interposing a medium through which only fluid can pass is dash. So it's a filtration process, right? Definition of filtration. So here the oxidation is, can you tell me what is oxidation? Anyone? Can you tell me what is oxidation?
Addition of oxygen, removal of hydrogen.
Yeah. So any reaction with oxygen to form oxidate, like final product which adds up oxygen or which removes hydrogen, that is oxygen, right? Oxidation, sorry. What is distillation and absorption?
Distillation is the process of separating the two liquids.
Yeah, and what does it use? Like, you are very right. So it uses
Fraction.
the phenomenon of difference in the boiling points, right? So
Yes.
if more the boiling points are different, it easily will be separated, right? And another is absorption, where sorry.
One absorbent medium is used. For using that absorbent medium, you have to separate the solid material present
Yeah,
in
so it
our
will
water.
get, basically it will get absorbed,
Filtration.
or yeah.
Removal of
And
solute from solid by using liquid solvent.
yeah, yeah, correct. So basically, you can say it will all. You can also say that it is getting dissolved, right? So yeah. For example, if you want to separate a mixture of sand and sugar or salt, right? So how can you do? Uh, you can dissolve sugar in water, and sand will not be able to dissolve. So uh, you can dissolve sugar, and later you can evaporate or evaporate water, and also you can recover the water by condensing it, and whatever the solid amount left will be sugar, right? So you can separate sugar and sand by this manner. And last question is, in dash filtration method, the removal of suspended particle material from liquid slurry is done by passing the liquid through a filter bed composed of granule or compressible filter media. So the correct answer is depth filtration, right? Is it clear so far?
Yes, ma'am.
Okay, so if you have any more doubts, you can let me know. Otherwise, I can end this class for today.
Where I get more practice question for this course paper, ma'am. In net, it is available, ma'am, for each and every unit, sedimentation, filtrations.
What sort of questions do you want to practice numericals?
That is, so the SEM exam is based on like our assignment question, ma'am, or it is completely different?
Yeah, so exam will be based on like your assignment questions only. So not this week, but if you have any doubt in your previous week assignment, you can come take and let me know. Like not this week especially. So previous
Okay.
weeks 1 to 5 you can come with doubts in the next class maybe. And yeah, so similar questions you can expect. And for example, if you are getting any numerical in that assignment, you can, what you can expect in the examination is some changes in the values, right? Otherwise the pattern might be similar or so. And yeah, theoretical questions similar to what we are solving in the assignment and the classes as well. So similar questions you will expect.
Okay. 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 Thank you. Any previous year SEM question is available, ma'am?
Previous year exam question, yeah, I
Uh,
guess that is not with me, but still I will check, and if I have, we will let you know.
okay. Thank you, ma'am.
Again, if you want to practice more questions, I will see if I have access, because I am also like don't I also don't have access to all the things. Uh, I will check if I have access to more questions so that I can get you more practice done. So I will check that and get back to you on this in the next class.
For more numerical problems, you are concentrate. You can take the other questions. I can see you can solve it in a class. Means it will give the better idea to solve the
Yeah,
same type of
actually,
problems
yeah.
in
So
our
the
same exam.
yeah, so these questions are also like model questions which are provided to us, which we are supposed to solve in the class, right? So I will check if there are more numericals. I will surely discuss more of it.
Okay. Okay.
I will check if I have the access to those.
Okay. Ma'am. Okay.
Sure.
Thank you.
And you can come for take your assignment questions if you have any difficulty solving. You can take those questions during the next class, like the previous ones, right? Not the current week's assignment.
From
That you
one
need
to
to
five
solve them.
assignment, I can take it and then come to the next class.
Yeah, so
Okay.
1 to 5 you can take and come in the
Okay.
next class.
Okay.
Okay. So should I end the class for today?
Yes, ma'am.
Okay. Okay.
Thank you.
Thank you. Thank you
Thank you.
for